1, 2, 3. Okay, great. Let's see, can you see these slides? Okay, great. All right, so hello, everyone. Good to have you again. We're almost done with the semester. Next Tuesday will be our last lecture. And, you know, I haven't seen you in person since, you know, the coronavirus pulled us apart. And so, but I'm happy to see your faces even digitally. It is very important that you attend next week's lecture. It's unlikely there will be a lot of material covered depending on what we cover today. So I'm going to try to get everything out of the way today so that next week there will be a couple of activities that we will do together. Typically, there will be also a lot of chocolate being distributed, but I'm just going to send you digital chocolates. Or you go buy a chocolate and eat it. So, but we will also do the feedback, and then there's something that's been the hallmark of all my courses that I do with my students every year. So you'd have to come and see to be able to participate in it. It's pretty cool, I think. And also another thing that we will do together, and then, you know, I'll let you go. The final exam I made, I changed the front page, I made an announcement, I sent individual emails to make sure. I always get complaints like, you know, someone didn't receive the email or didn't receive the announcement. So I'm trying to make sure that everyone is getting everything right. Hello, Jeff. Good to hear your kids running around. All right, so make sure that you see those. There's only 31 students here. If you know someone else who wasn't here today, just make sure, tell them, hey, did you know that the exam is going to be Friday, the April 24th? There was a confusion on my website. It said April 23rd. But that was a mistake because the course was scheduled to be Monday, Wednesday, Friday. And I don't set the final exam date, the university sets it. And for our class, go ahead and verify for yourselves on the registrar's website for classes, Tuesday, Thursday classes that start at 2 p.m. The final exam is scheduled on Friday, April 24th from 1 to 3 p.m. Okay, the other thing is, I want you to all be available on Zoom with your camera on, microphone, sure, but I want to see your face, see you working on the exam. We're not going to be using ProctorU. We'll just be using just this, and you'll see my face. I'll be around, and Mokbel and Bailey will also be around. But I also asked you to do a quiz, confirming and acknowledging that you know the exam date and you have a camera ready. You won't be able to get into the exam if you don't go on Zoom, because I will post the access code on the screen. So you have to be here, I have to see you, and then you'll be able to access the exam, okay? So make plans ahead of time that you can have some, you know, the space you're gonna be working on in, at least you have your camera, etc. Everything set up, okay? And there's only 33 participants today. Make sure you spread the word, because I'm not sure people are getting emails, announcements, changes. I don't know what else to do. Carrier pigeons, I suppose. Anyway, so please tell your colleagues and friends, spread the word, okay? That being said, we're gonna finish off with boundary value problems today. There'll be 3 things that we will cover. We'll finish off with the fixed boundary conditions case, and we'll give that a name, and then we will do something together. We'll do a problem together in Python. Then we will change one of the boundary conditions. Rather than specifying the value at the boundary, we're gonna go and specify the derivative. Rather than the value of temperature, we're gonna specify the derivative of the temperature, which is equivalent to a rate of heat that's coming in, rather than fixing a temperature at the boundary. And then we're going to solve nonlinear boundary value problems, which would be kind of the ground achievement for the course. I remind me if I'm wrong, but I think we left off at this slide last time. And if you haven't had a chance to review this, go ahead and just kind of flip through your notes. But just to kind of remind you what we did, we started with the heat equation applied. Let me show you that heat equation. We started with the heat equation applied on a rod that is heated on both ends, and the equation that governs the heat transfer inside the rod. We're looking for the, so heat can be described by temperature, obviously, and one measure of heat is temperature. And so therefore, we describe the heat transfer equation inside the rod as the heat moves, as the particles, molecules vibrate and transfer that energy to each other. That is measured as temperature, and the equation for the temperature across the rod is given by this equation. Second derivative for the temperature along x is equal to some coefficient, we call that capital H, times the temperature of the rod at any point, right, minus T infinity, which is the surrounding temperature. Now the surrounding temperature, the air, we said, or the liquid, whatever is around the rod, is going to be either contributing to heating or cooling the rod. And the rod is fixed at both ends, physically, perhaps, but more importantly, the temperatures are fixed at both ends. So T at the left-hand side, at the left end of the rod is T left, and T at the right, we're going to call that T right, okay? And then we went ahead and discretized and did a bunch of fun things, and we ended up arriving at a linear system of equations. So again, we're trying to solve for the unknown temperature values at the discrete points in the rod. We took the rod, we said, let's divide it into discrete points. We'll apply the governing equation there, and then we discretize it. We get a linear equation between the variables relating the temperature at point I to the temperature at I minus 1 and the temperature at I plus 1. And you know that formula up at the top here, that's the template for what the discrete equation looks like at every point inside the rod. At the boundaries, we have a different equation because we're given the temperature. There's no equation to solve. In other words, just T1 is T left and Tn is T right, okay? We all agree on that, and then this is where we left, I think. Now that you see a system of linear equations, actually, this is our first activity. I want you to go ahead and write this in matrix vector form. So remember, you're gonna have a coefficient matrix, pardon me, and I predict that it will have a lot of zeros in it, and multiplied by a vector of unknowns. What is that vector of unknowns? Going to be what? T1, T2, T3, etc., equal to something on the right-hand side. Okay, so go ahead, got a couple minutes. Do it for yourself. So just basically transcribe these equations into matrix vector form. You have the equations. This is the system, and we are solving for T1, T2, T3, all the way to Tn, okay? We've got about 45 seconds, and you should see a structure emerging. Okay, time. All right, let's see. Paul, do you have an answer for us? I know it's hard to describe the matrix, but at least can you give me a couple of elements on the matrix?
I think it's a tridiagonal matrix.
Correct. And the first row of the matrix, give me the first row.
It would just have one and a bunch of zeros.
And then a bunch of zeros. And what's the solution vector? What does it start with?
The right-hand side?
No, the unknown vector. So at equal b. What is t, the vector?
It is t left.
No, t1. The right-hand side is t left. Okay. All right. So let's see. For the second row, let's see. Prasanna, do you want to give us the coefficients in the second row?
The second row, that would be, would that be T2 to Tn?
No, the second row of the matrix, the coefficient matrix.
Oh, T1 to Tn?
No, that's the solution vector that we're trying to solve for. So ax equal b. I'm asking for about a. So
oh, sorry, that would be 1 and then negative 2 plus h delta x squared, and then 1 again. And
okay,
then
and then a bunch of zeros. And so this describes which equation that I'm showing here on the slide?
The heat equation? I'm not
No,
sure.
which one of those equations that I have listed? Yes, I see an arrow. Who's writing the arrow?
That was me.
Who was that?
That's Eric. That's me.
Okay, Eric. All right. I knew you knew the answer. That's why I didn't ask you. So Prasanna, did you see that? That
Yeah,
the row, corresponds to the second equation, and then so on and so forth all the way to the end. So here's the matrix. The way, again, you think about this, a matrix, a system of equations in matrix form is just a set of equations. Over here, equation 1 is simply 1 times t1 equal t left. It just tells us t1 equal t left, which is great, right? So although we said we know t1, we incorporated t1 into the solution matrix because programmatically it's going to be easier. You'll see later. But it essentially just gives us t1 equal t left. The second equation is t1 minus parentheses 2 plus h delta x squared t2, right? Plus t3 equal minus h delta x squared t infinity. The third equation for point 3 all the way to the last point, okay? Now, I claim that you know how to solve this. This is, like Paul said, a tridiagonal system of equations. Now, we use the Thomas algorithm, we can use that, but we don't have to right now. We're just gonna build any solver in Python. But I want you to know that I want you to remember that you know how to program this matrix. So the cool thing over here with what we did with the heat equation is that you have to program the matrix, and that coefficient matrix and the right-hand side change depending on the governing equation, right? So whereas with ODE int, what we did was just give it a right-hand side and it did its thing automatically. This is different over here because it's a boundary value problem. It's going to depend on the discretization you're doing and the structure of the matrix, the right-hand side. So you're going to have to program the matrix yourself. But what I'm saying is that you actually know how to program this matrix because we did this way early on in linear systems. Who doesn't remember that? I thought you were all traumatized by linear solvers that there's something to remember, at least the trauma from linear solvers. But if you remember, because this is such a simple matrix, it's mostly non-zero, all we had to do was program the diagonals as one-dimensional arrays, right? Using mp.1s and multiplying that and fixing values, and then combining all of those using diag, numpy.diag, to create a matrix, okay? I don't know if you remember that, but you should, I hope, because next you're going to have to download this boundary value with gaps, and I'm gonna ask you to program this matrix. So on Canvas, there is boundary value problem example, heated rod with gaps. Okay, so go ahead and download that notebook. Some of you already downloaded that last Tuesday. We never got to it. Okay, so just go into Canvas, and there's under Jupyter Notebooks, there's the boundary value example with gaps.
Is the Jupyter notebook different at all from the one that was
No, I didn't change it. So we didn't touch it, and I didn't have to change it. So your activity is going to be to build the coefficient matrix and the right-hand side for this system of equations. I want the user to specify the number of points. This is nothing different than what we did at the beginning of the semester, right? Except here, you are responsible for deriving the matrix. Okay, with linear, when we were doing linear solvers, I gave you the matrix and I told you just solve it. Now you're responsible for deriving the matrix and solving it, okay? But more importantly is getting the matrix, because that will give you, the recipe for the solution, okay? And then the spacing delta x is obtained by creating a lin space, and then solve it and plot the temperature versus location on the rod. So I'm gonna escape the slide now. I know you need to see the equations, but please go ahead and download the PDF from my website. And I'm gonna open up the boundary value problems with gaps. Okay. Rod with gaps. Let's see. Okay. Actually, it's programmed right there for you. Okay. All right. So what I have here is, again, the standard boilerplate. Let's make sure everyone who doesn't have the notebook downloaded and ready. Does everyone have the notebook downloaded and ready? Okay, excellent. All right, so let's go ahead and run this boilerplate. What I do, I just copy this through all my notebooks and never have to worry about it. Feel free to do the same. Okay. All right, so what I have here is, first I define the number of desired grid points. So these are the number of points, not the intervals. Okay, so these are the number of points starting from 1 to n. Okay, I say 200 points. My L, the length of the rod is 1. And we're going to play with temperatures over here in a second to understand the physics of the problem. But first, let's just assume that T left and T right are both at 300 degrees, and T infinity is at 500. Now, what does this mean? T infinity is higher than the temperatures at the left and the rod. So are we cooling or heating the rod? Eric?
It means you're heating the rod because the surrounding temperature is higher.
Yeah, exactly. Now, this H coefficient, I suppose I need to make it capital H. Okay, this capital H coefficient, we said last time, determines how effective that heating is or not, right? So if you blow air at the rod versus if you draw air at 500 versus oil at 500, which do you think is going to heat the rod kind of more effectively? It's going to be the oil, because it conducts heat better, okay? It allows heat to be transferred much faster. And we'll see that effect by modifying this coefficient H. Right now, keep it at 1, okay? Next, we're going to create a linear space. Like, this is exactly the procedure we followed in the slides. First step was to discretize the spatial domain. And we need this because we want to plot temperature versus X, right? So we want to plot the temperature versus each location on the rod. So go ahead and create a lin space starting from 0 to L with however many points. Feel free to chime in, help me. So first item here. Eric, do you want to guide us through this? You want to guide me through this?
I can help.
Okay, go ahead.
So you're going to have 0 for the first one, and then L for the second.
Good to see you, Tyler.
Yeah, and then N for...
Okay, N, that's right. I put 200, I should put N. Excellent. And then the spacing is simply obtained because this len space is equally spaced points. The difference between any 2 points is going to give us the spacing, right? So that's how I calculate the spacing. dx is the first entry in len space minus the second entry. Remember, this is an array. And if you're confused about it, just simply run len space, 0 to 1 with like 10 points. It's going to give you an array of points. And the spacing between any 2 points is actually delta x. Okay. Now we want to create the lower diagonal vector. So that's the lower diagonal. It's all ones except for the last entry. Okay. So, all right. Anyone wants to help me with this?
I can try.
The recipe is right here for you.
So for the lower diagonal, so it's
Katrina,
all
do you
ones.
want to help me? I can't hear you.
Yeah. Okay. So
I can't
all
hear you.
ones besides the
You're
last one.
unmuted,
So
but
I just put
looks like
in.
your audio is not working.
Oh really? Is it working now or?
I can hear her.
I can hear her.
I could hear Katrina
Henry,
really loudly.
Okay. So I just put np.ones.
Sorry. For some reason, I was muted.
Okay.
I apologize. All right.
Anyway.
I don't understand technology. It's okay. Lower diagonal. Katrina, go ahead.
Yeah. So I put np.ones and then 200 if we specify n as 200 points.
So why 200? Why not use n?
Oh yes, n. Yeah.
But is it n or less or more?
Just n. But then you specify the last point, so then you put in like lower
No,
diagonal.
so I disagree. It's not n.
Oh, okay.
The main diagonal has, yes, Eric.
Be n minus 1 because it's the upper diagonal.
It's the it's the lower or upper. Yeah, they're the same, right? So they're one size less, right? Because the main diagonal is n, but then the lower and the upper they're n minus 1. Okay, and then we change the endpoint by
colon and then -1.
Why colon?
Oh yeah, never mind. No colon.
Just -1, right? Because it's a one-dimensional array, and we make this one 0, right? So that's the last entry over there. Okay, now the main diagonal. Emily, do you want to take that?
Sure. So for the main diagonal, I have np.ones of length n. So that's how big our matrix is. And then times by the minus, times by -2 plus x squared h.
X squared?
Delta x.
Yes. Okay.
Yeah, sorry,
dx,
delta x
times
squared
h.
and then h.
Okay.
And then the 0th entry and the last entry should just be 1.
Exactly. Okay. Upper diagonal. I'll take this now that I learned from you. Is np.ones n minus of size n minus 1, and we're going to fix in this case we're going to fix the first point, not the end point, because the first point is going to be 0. So we're going to put upper diagonal 0 is equal to 0. Okay. Pardon me. So now I claim that we have the entire matrix. Eric, do you want to take building the diagonal, the full matrix using diag?
Yeah, so on that line, we'll have a equals np dot diag for lower diagonal at -1.
Correct.
And then np dot diag d at 0. Np dot diag ud at 1.
At 1. Excellent. And then, all right, so let's see. I'm done with the first set of people on my screen. I'm going to scroll to the next set. All right, we have Henry next. Do you want to help us build the right-hand side, Henry? So the right-hand side is this vector over here. Henry? Okay. Jeff, you want to take a stab at it? I can't hear. Let me unmute you. Okay.
Sorry, can you hear me?
Yes, I can right now. Okay. So it's a vector of size n, so definitely it should have np.ones of size n, right?
Yeah, and then you can just multiply it by t inf times dx times dx
Excellent.
times h.
Thank you. And then we'll fix the first and last entries by saying this is t left for the first entry and the last entry t right. All right. Okay. Garrett, do you want to take this next line, solving it?
1 sec.
So we build the coefficient matrix A, and the right-hand side, we call it right-hand side. And yeah.
You just do A comma RHS.
Correct. Yes. And then we claim that this will solve. This will give us a solution, and that solution represents T1, T2, T3, all the way to Tn, correct? And then we're going to plot that solution versus X. Abigail?
Yeah, so you'll just put in X and then solution.
Excellent. And let's hit Shift Enter. Ta-da! Look at that. Isn't that cool? Okay. First thing you check, look at your boundary conditions. Is the first point and the end point, are they 300? From this point, from this plot, yes. So at least you have confidence in your matrix setup. At least you're getting those endpoints right. You could try changing, let's say, let's put the left point at 400, run it again. Look at that. At the left point, we're at 400. At the right point, we're at 300. Okay, let's change it. Let's go 300 for the left point and 400 for the right point. Same thing happens. Okay. Now I'm going to go back to 300 and 300. I'm going to leave T infinity at 500. Now I'm going to look at H. So H1, this is what we get, right? H equal 1, this is what we get. Looks like a parabola. What if H is equal 10? So we said that H tells us how effective is this heat transfer coming from the air or the fluid, okay? Okay, so notice what happened. It's hard to see right now, but what I'm gonna do, what happened is we increased the temperature. It went up to 420. So what I'm gonna do, I'm gonna change the limits, plt dot y limit, okay? It's gonna be, let's say 300 to 500, okay? Just to kind of set the stage a little bit, okay? T infinity is 500, and the other temperatures are at 300. So this is what happened at H equal 1. We barely got up to 325 in the middle of the rod, okay? As H increases, we went up to 10. We were able to heat the rod up to 425, okay? Can you see this? Now, if H is 100, so that's a higher heating fluid. Look what happens. We reach 500 very quickly, and then it starts kind of spreading across the rod. So previously, it was more concentrated along the center of the rod when H was small. So for H equal 1, heat was kind of parabolic and mostly concentrated at the center of the rod. And even if you go to H equal 10, this is what you got, right? But then as H climbs, so let's go to 100, you heat it up to the temperature. Remember, 500 is the temperature of the incoming fluid. And we cannot heat it any more than that because of conservation. Okay, when T is equal to T infinity, the right-hand side is 0. There's no more rate of change. That's what the ODE tells us. Now, let's go to 1000. We expect the heat to be spread. Look at that. We expect the air to heat up the rod almost everywhere, right? So that's why we use like fluids with higher heating ability, right? So that's why you want to cook in oil and then maybe water, and then the last thing is you want to do in air, right? Because oil and water, they're more effective at, they have a higher heat transfer coefficient, okay? Is this clear? Is this kind of just resonates a little bit, gives you some sense of what's going on? Okay, now let's take the opposite. The opposite is going to be true. So let's say we cool it, okay? Let's say you want to go to, oh, one more thing. What if H is very small? Okay, so let's look at the governing equation. What if H is very, very small, almost 0? What do you expect to see? If d2t by if H is 0, what happens to the governing equation? Some people chatting. Just feel free to open up the mic.
The temperature will barely change in the rod.
Yes. Well, can you qualify that a little bit more? So for this case, if both temperatures are equal at the left and at the right.
So the middle of the rod will be closer to the temperature of the left and the right.
Okay, so if they're equal, if H is 0, there's not going to be, the right-hand side of this equation will be 0, okay? So as H approaches 0, the right-hand side of the equation will be 0. What you said is correct, but let me kind of generalize it. And therefore, the solution will be just a linear change between T left and T right. Because it's a second derivative equal to 0, then you integrate it twice, gives you a straight line. So you'll see a linear change in temperature from the left to the right or from the right to the left, however you like it. Okay, so let's see, let's verify this. Let's go for H equals 0. 0.0. We expect here to, essentially for the temperature, look at it, it's right over here. If you can't see it, there's like this blue line. All the values of solution are actually, so if I print solution, they're all 300. Okay? Okay, so with H equals 0, if T left is 500, I predicted that this will be a straight line. Indeed, it's a straight line because the solution to a second derivative, you integrate second derivative equal to 0 twice, you get a straight line, right? And that's what you expect. So all of these tell me that my code is bulletproof and it works, okay? Now let's look at the other extreme, other end, where we're cooling the liquid, and I hope that you will agree that we'll just get similar behavior but opposite curve. So let's say the liquid is at 100, and I'm going to go from 100 to 300 for the plot limits. Now we see that the temperature is dropping in the middle. So imagine initially the entire rod was at 300, and then you cool it. So we were able to only drop the temperature down to 275. If we increase H, we'll be able to cool it faster. Not faster, there's no time in here, but we'll be able to more effectively get the heat out. Okay, look at that, we dropped it to 175. If we go to H equal 1,000, it's pretty much gonna be the temperature of the fluid, which is 100. So now you have a sense that these things actually describe reality and they give you some sense of predictability. So, when you're thinking, you're gonna take a heat transfer course later on, and you'll be able to kind of see these things. The next cell I have over here is just a cool visualization for you to see kind of in terms of colors, where blue is cold and red is hot, where you see how this, just to visualize the heat transfer. So if we go to H equal 1, we see cooling in the middle, but then it's hotter on both ends. And the opposite is true. If we go to, let's say, 500 heating of the middle, then you see it hotter in the middle, red, and then cooler on the end. Just a little trick to play around with. All right. Would you like to make any comments? Katrina, you have a comment? Okay. I thought because you unmuted, I think. Oh, no, sorry. All right. If there are no comments, we are gonna call this a victory over the first type of boundary value. What we discussed here, the type of specific boundary condition we discussed here is called a fixed boundary condition or a Dirichlet boundary condition. Let me spell that for you. So what we just covered Dirichlet or fixed boundary conditions, okay? And I had a little slide over here.
Where were you typing that?
I will share it with you in a second. I'm typing it on my slides. Okay.
Okay.
All right. So what we just covered is called Dirichlet boundary condition, where the value of the dependent variable is specified at the boundary. So given this equation, for example, could be any equation. I mean, we're dealing with second derivatives here just because they're very popular in transport, but you could have a first derivative and you would just discretize it the same way we did, okay? But what's important is when you're given a fixed value of the dependent variable at the boundary, what you're gonna, that's called a Dirichlet boundary condition, okay? Some guy left. Pardon me? Did someone say something? Okay, I thought I heard something. Okay, so now the other end of the spectrum, which we haven't covered yet, is called Neumann boundary condition after John von Neumann. And in that case, instead of specifying the value of the quantity of temperature, we specify the rate of change of that value at the boundary. It turns out that mathematically, it's kind of easier to deal with fixed value boundary conditions, but physically, observationally, it's easier to maintain a rate rather than a fixed value. So just like a flow rate, for example, it's easier to maintain a flow rate rather than just a certain volume of liquid at a boundary. So same thing here. It's easier to maintain a flow of heat, if you think in terms of the heat equation, or a flow of a concentration or a chemical or a pollutant. Well, you don't want to maintain a flow of it unless you're extracting it of a pollutant, but it's easier to maintain a rate of a pollutant or of a quantity at the boundary, okay, physically, many times. And that type of boundary condition is called Neumann. But mathematically and numerically, it's a little bit harder to solve. But together, we will be able to attack it, okay? All right, so Neumann boundary conditions. I hope you're with me now. All right, so we're gonna take now the same problem, same thing, same discretization, nothing changes. The governing equation is the same, the discretization at the interior points is the same, the condition at the left at a fixed boundary is the same. What I'm gonna do here, I'm gonna keep the left boundary fixed, so T1 is equal T left. However, I'm gonna change the right-hand side, the right boundary, and I'm gonna make it a rate. So instead of specifying T at point N, just like we did previously where we said Tn is T right, now we're gonna say dt by dx at n is equal to some quantity. So think of it as you're supplying a fixed rate. So I think this is how ranges, electric ranges work. They just supply a fixed flux, a fixed heat flux. Okay, so that's what you're doing here. You're supplying a fixed rate of heat, dt by dx. It's a rate of heat, right? It's a rate of heat coming into the rod. So here, this is given to you. So we know, rather than knowing Tn, we know dt by dx at n equal to beta. Beta could be a number. It's a number. You know that, okay? But, however, that has serious implications on how we're gonna apply the equation. So, because we don't know the temperature, the only thing we know at that point is dt by dx, and also we know we're going to assume that the governing equation applies at that boundary point, okay? Remember, the purpose of the governing equation is to give us T. On the left-hand side, we know T, so we don't need to apply the governing equation at that left point. But on the right-hand side, on the right side of the rod, we don't know T. So we're going to go ahead and apply the governing equation, okay? So we're going to discretize the governing equation over there. So go ahead and try to discretize our governing equation, d2t by dx squared equal whatever. If you try to do that, and if you remember our formula, you're gonna need, so at Tn, you're gonna need Tn, you're gonna need Tn minus 1, but you're also gonna need a point that doesn't exist, point Tn plus 1. Right, so if you trust our governing equation, and there was an h here, I didn't have time to change the nomenclature, but hp over lambda ac is capital H, okay? So our governing equation used to say Tn minus 1 or Ti minus 1 minus 2 plus delta x squared h Ti plus Ti plus 1 equal h delta x squared T infinity negative. Okay, so we're gonna apply that at point n. That is gonna produce a point n plus 1. But there's no n plus 1. Agreed? Is there an n plus 1 here? We don't have an n plus 1, okay? Because we can do whatever we want. We're gonna create a fictitious point and call it Tn plus 1. That point doesn't exist in reality, right? That's not part of the rod. We're going to imagine, though, temporarily, for the sake of the numerics, that that point exists, okay, as a placeholder, just to allow us to get rid of it eventually. Okay, so we're going to allow a placeholder to exist. We're going to call that ghost point. It's not part of the rod. It's just an imaginary point, but we're going to use it as a placeholder to help us with the algebra. It's going to work beautifully. So next, what we will do, now we have this extra equation here that has this equation that has this extra point that we don't know. So we need somehow to eliminate that point. Otherwise, our system of equations does not work, okay, because we have more unknowns than there are equations, right? So we cannot solve the system of equations. We need a mechanism to add one more equation to eliminate this Tn plus 1. Can you suggest an equation that we can use, an extra equation that we can use to eliminate Tn plus 1? It's right there on the slide in front of you. Yes, Eric.
Method?
Pardon me?
Newton's method?
We don't need Newton's method. We have an equation. That gives us Tn plus 1. Pardon me?
You can use the differential, the delta Tn over delta x equals beta.
Yes, dt by, yes, we use the boundary condition. The only thing we haven't used yet is the boundary condition at point n. That was Dylan, right? Yeah, thanks, Dylan. So we only use the governing equation, but there was one equation that was given to us, dt by dx at n is equal to beta. We haven't used that equation. So what if we take that equation and discretize it to find a relation between Tn plus 1 and the interior? So remember, we're trying to eliminate Tn plus 1. If we express Tn plus 1 in terms of any of the interior points, we are good to go. Because our system of equations goes only from T1 to Tn. Okay, we have n equations and n unknowns. N plus 1 is an extra unknown, but if we can express n plus 1 in terms of any of the other points, we're good to go. Turns out there's this extra equation that was given to us, and like Dylan said, we're just gonna take that equation and we're gonna discretize it, okay? Do we know how to discretize it? Yeah, it's the first derivative. dt by dx at n is equal to Tn plus 1 minus Tn minus 1 over 2 delta x, and that's equal to beta. Now everything is in red is essentially this extra point that we want to eliminate. Okay, are you with me so far? Okay, are you with me? Okay, so this Tn plus 1 is in red. We are trying to eliminate it. We want to get it out of the system. Now notice here for this derivative, what order did I use for this method, for this discretization of the first derivative of the boundary condition? Is this a first order or a second order discretization? It's
second order?
Yes, thanks, Garrett. So why would I use a second order discretization rather than a first order? We could have said Tn plus 1 minus Tn over delta x, right? That's a valid approximation, or that's a valid approximation for a derivative, right? So why did you use a second order one?
Is our original equation like above where it says
Yes.
Tn minus 1 such and such is already a second order?
Yes, good job, Emily. So what Emily is saying is, because we used a second order discretization to discretize the second derivative for the heat equation, we need to remain consistent. Otherwise, we will introduce an error that will destroy our solution. So a chain is as weak as its weakest link. So even if you have at every point a second order accurate formula, you only need one point that is first order to destroy your global order of accuracy. So we need to make sure that the error introduced in discretizing this boundary condition is at least of the same order as the rest of the domain. We could use higher order. It doesn't matter because that gets flushed away, okay? So now see what happens. We have these two equations, right? And we have the second equation with Tn plus 1. We're gonna eliminate Tn plus 1 from it. We're going to express Tn plus 1 in terms of beta, which is known, delta x, which is known, and Tn minus 1. That's part of the system of equations anyway, right? So all we have to do now is substitute Tn plus 1 back into our equation. And then that last equation at point n, okay, becomes just, it changes slightly. The coefficient only at that last point changes because of that Neumann boundary condition. Notice, for all other equations inside the domain, we had a Ti plus 1 over here, except for this last equation, okay? Except for this last equation. All right, I'm sorry about the HP over lambda AC. That's H. We're calling that capital H in our system, okay? So to summarize, for a problem that has a Neumann condition, and here I gave you the example of one Neumann condition at the left. You could have two Neumann conditions on the on the right. You could have one on the left and one on the right, or you could have only one on the left, but the same methodology applies, okay? So for this system, at point 1, the equation is T1 equal T left, like we saw earlier. For all other points in the domain, we have Ti minus 1 minus 2 plus H. It should be delta x squared over here. Ti plus 1, and then equal. So there's a typo here. I will update the slide for you. There's a typo here. There should be a delta x squared over here multiplying H. Okay, plus Ti plus 1 equal minus H delta x squared T infinity. Okay, and then the last equation is only different because this Tn plus 1, we expressed it in terms of beta and Tn minus 1. Okay, now in a system of equations, we put everything that we know on the right hand side. So notice how I moved beta delta x to the right hand side, and everything everything that we are solving for on the left hand side. Okay, the next slide has the correct equations. Okay, now when you're deriving this in the exam, all interior points will be the same. So you need one equation for the interior points, one equation for the left boundary, and one equation for the right boundary. Okay, start with the equation in the interior points. And then when you reach the boundary, think, do you have a Dirichlet? Then I know temperature. If I don't have the Dirichlet, I'm going to eliminate. And you only need to change the discretized form only for the last equation, okay? Now, when you express this in matrix form, it's still tridiagonal. And notice it looks exactly like the equation we had before, okay? Except for the last equation. There's a 2 over here. Notice the coefficient for Tn minus 1 changed because we added an extra Tn minus 1 from that Neumann condition. And this guy remained the same. But what happened on the right-hand side, we have a minus 2 beta delta x, okay? So this is more like an exercise. The key here is you're recognizing how to incorporate a Neumann condition into the system of equations. There's nothing different than what we did with the Dirichlet case, except for that last equation, okay? Or it could be something on the left. So we'll do an example now. I'll have you do an example. We're going to consider this governing equation. And notice I'm changing the names of dependent variables on purpose because I don't want you to be confused on the exam if I call my dependent variable y, or if I call it, pressure, or, gamma. Don't be confused. Here I'm calling it u. The governing equation is d2u by dx squared equal x squared u, okay? And you are given two boundary conditions. Now you have a Neumann condition on the left, okay? It's du by dx at x equals 0 equal alpha, okay? And a Dirichlet condition on the right, un equal beta. I cannot give you, don't use a general formula to apply this. Every time you have to derive it. Derive it a few times, and then you'll get a sense of what the general template is, okay? So we're gonna derive this together. And note the numbering. I started from 1 all the way to n, okay? So that you have a ghost point called u0, all right? So at an interior point now, I want you to write the discretized equation at an interior point I. You got 1 minute, okay? Feel free to use the slides posted on, I'm gonna leave the slide here in front of you, but use the PDF slides or whatever you have from your notes. You got about 10 seconds. All right. Okay, let's see. Barak, do you have an answer?
I was not able to get this one.
Okay, let's see. We'll help you get it. Alex, do you have an answer? Fabian, we got 2 Alexes.
I actually don't have one either quite yet.
Okay. Okay, one last choice. Let's see. Jordan, Payne.
No, not yet either for me.
Okay. So, any volunteers?
I'm not certain if this is right, but I'll give it a shot.
Okay.
So I have u of I minus 1
Mhm.
minus the quantity 2 plus delta x squared times x squared,
Mhm.
quantity times u of I
Mhm.
plus u of I plus 1 is equal to 0.
Yes. Okay. Good job, Emily. So first what we do is we discretize the equation as is. So the second derivative is ui minus 1 minus 2 ui plus 1 over delta x squared. You know, you do that often enough, it just becomes part of your mind. On the right-hand side, simply apply that right-hand side at point I. It's xi squared times ui. Or you simplify it like Emily did, and you get ui minus 1 minus quantity 2 plus delta x squared xi squared into ui. Remember, delta x, xi are known, right? We just learned how we do xi, so linspace, right? It's given to you. Plus ui plus 1 equal to 0, okay? All right, next, at the left boundary, I equal 1, what is, we have a Neumann condition, right? So what is the discretized equation at the Neumann boundary, all right? So I'm gonna have to figure out how to show you the slides with the Neumann. Give me a second here. Maybe I'll copy the slide and show you what we did. Hold on. Okay, so first, I guess write the equation. I'm gonna copy the Neumann solution that I did. Just a second for you. These activities can get very complicated. Okay. So remember, we first wrote the discretized equation at that point, and then we tried to eliminate at the left boundary. Okay. Okay, yes. So this is it. I'll give you a minute. You already started, I know. So at the left boundary, what we did previously, we wrote the discretized equation at the Neumann boundary. So not left, right, doesn't matter. We wrote the discretized equation at that boundary. We had a ghost point. So write it at the Neumann boundary. Don't eliminate now. Don't eliminate the ghost point, okay? Just write the discretized equation at the Neumann boundary. I suppose I already had that kind of in front of you, right? Because you have the discretized equation right there. Let's see. All right, I'm gonna call this time. Okay. Excuse me, Amber, do you have an answer? Just the discretized equation at the left boundary with the ghost point.
Yes.
Yes,
So
what is it?
du dx at x equals 0 is u2 minus u0.
So no,
2.
that is not the discretized equation. That's the described boundary condition. So you are ahead of us. I want the governing equation discretized and expressed in terms of the ghost point. So essentially, what I have just in front of you, what I had written just in front of you, in terms of the ghost point. Does this make sense? So in other words, this formula, ui minus 1, ui plus 1, at the left boundary, what is that formula in terms of u0? Nick?
Sorry, I'm still working out the solution.
Okay, let's see, Kevin? Nope. Okay, all right, let's see. Isabel?
Yeah, I'm a little confused still as well. I'm gonna need a sec.
Okay, so take this equation where my cursor is kind of hovering around and apply it at point 1. Simply put I equal 1. What that is going to give you is u0 minus 2, etc. into u1 plus u2. Okay? We said we don't have any value for u, for the dependent variable at that boundary. So we're going to apply the governing equation there. And we're going to create a fictitious point, u0. Okay? And next, we're going to worry about eliminating u0. So now we've introduced a new unknown into the system, but we're going to use the boundary condition to eliminate that unknown, which is your next activity now, which I suppose Ember just answered. So Ember, do you want to give us, actually, let me give you a minute to go through it. So discretize the Neumann condition, okay, at that point, and then substitute back into this equation at point 1, okay? I want to see the resulting discrete equation at point 1. So this is, if you're not getting this now, which is understandable, make sure you revisit this and you get the same answer, because this will be on your final exam. Okay? It's not a secret. All of what we're covering now, you're gonna be responsible for it for the exam. Should the ghost point, in this case, u minus 1, but then we just shift everything over. Why? Okay, got it. I'll get to your question in a second, but since we started numbering from 1 to n, you know, our extra point, it makes sense to put it at 0, right?
Okay, so if we had started numbering it like u0,
yeah,
I
then
guess,
you would be
then
u
it would...
minus 1. I mean, you
Okay.
could call it whatever you want, right? Yeah, but just to be consistent with the numbering, yeah, because we started at 1. Okay, so we'll start with Amber. She had an answer for eliminating the how we're going to eliminate this point. Amber, do you want to give us how you discretize the boundary condition?
Well, I had said, I was just thinking actually about, I hadn't taken this step. I was just thinking about the slope at that endpoint. So du dx at x equals 0 is u2 minus 0 over 2 delta x.
Yeah, that's it. That's exactly it. It's u2 minus u0 over 2 delta x, right? So now we related u0. Remember, we're trying to get rid of u0. And getting rid of u0 means expressing it in terms of anything else in the interior. u1, u2, u3, whatever, right? So the simplest second order formula would be u2 minus u0 over 2 delta x. But also know that that's equal to alpha because that's given to us. Okay, that is given to us. So therefore, it's just standard. It's just obvious to extract u0 as in terms of u2, in this case, u2 and alpha, right? So now you just take this u0 and put it in the above equation, right? There you go. So you get u2 minus, I just substituted u0 over here. I put it up here. You get u2 minus 2 alpha delta x. The rest is the same. And then you rearrange terms because we want to put everything we know on the right-hand side. So we get this 2 alpha delta x is going to move to the right-hand side. And then u2 is going to be augmented by 1 extra coefficient, right? And that's it. Now, at the right boundary, it's obvious un is equal to beta, okay? So now you have these equations. Go ahead and write the matrix vector form on the right-hand side for this system. You got 1 minute. You should get this right. I mean, you have the equations in front of you. There's the interior. The first equation here, this guy is for the interior points. This guy is for the first point. And this guy is for the last point. If you cannot express this as a matrix vector form, you have to review your algebra. By now, you should know how to do this. I don't mean to be mean, but this is something that you should just be able to do just right out the bat. Off the bat, I suppose. Okay, you got it. Couple seconds. All right, time. Okay, let's see. Katie, welcome. Do you want to take a stab at, yeah. Oops. Do you have an answer for us?
Or, sorry, I have at least the start of an answer.
Okay, go ahead. Let's start with the first row of the matrix.
Okay, so first row of the matrix would be the left-hand side. So I said the leftmost entry would be the negative 2 plus delta x squared x1 squared. And then the second one would be 2.
Yes, that is very important. And then
the rest of them would be 0.
Okay, and those first 2 coefficients, then they multiply which unknown u? Is it u2, u3, u1, u2?
It would be u1 and u2 because our solution vector would go from u1 down to un.
Yes, very good. And finally, what's the right-hand side for that equation?
The right-hand side would be the 2 alpha delta x.
Very, very correct, Katie. Okay, the rest is obvious, but the way to think about this is just the first equation, like Katie. So first, our vector of unknowns, what we're solving for is u1, u2, all the way to un, okay? Now start with the first equation. That's the one at the leftmost point. That's at point u1, right? And that equation has u1 and u2 in it. So the first coefficient would be the coefficient of u1. The second coefficient would be the coefficient of u2. And those are right here. Okay, and the right-hand side is the right-hand side of that equation. The rest of the coefficients, they're 1, minus 2 delta x squared, xi squared, and 1, right? All the way to the last point, pardon me, which is 0 everywhere, because it's 0 u1 plus 0 u2 plus 0 u3, all the way to 1 un equal to beta. And all the other right-hand sides are 0, okay? All right. Before we do an example, I'll give you a 2-minute break. But if you have any comments, feel free to open up the mic and start talking, okay? Go ahead, take a 2-minute break, drink some water, stretch your legs. All right, I am back. So before we proceed any further, let's just go ahead and do an example for this same problem that I have over here. We don't have any notes in the Jupyter notebook itself, but we're just going to go off the slides. Okay, we're just going to go off the slides and try to implement this, because with a Neumann condition, really the only thing that changed was these 2 coefficients in the matrix, or one of them on the left-hand side or the right-hand side, and the right-hand side over here, okay? So everything else is the same. So if you compare the Dirichlet case to this case, note that, and that I will fix this before I re-update the notes, the HP over lambda AC, we call that capital H in the Jupyter notebook, okay? So they are identical, except for this last entry over here, because in this problem, we had a Neumann condition for the heat transfer case. We had a Neumann condition over here. So we expect the last equation to be different. And notice the difference. Over here, we had 0 and 1. Over here, we have 2 and minus 2 plus delta x squared capital H, okay? And finally, on the right-hand side, rather than having a fixed value for the boundary, for the temperature, it's actually something different. One is delta x squared H T infinity minus 2 beta times delta x, okay? Just like we've derived here. So what we're gonna do now, we're just gonna take what we did here exactly. Just go ahead and Command A or Control A and copy it, and just add a new cell here and type Neumann boundary conditions, okay? Now, what I'm gonna do for, it's gonna be very annoying to do. Actually, I'll update the notebook and do it later, but we're gonna just go off the slides over here, okay? And what we're gonna do, we're gonna keep the same numbers over here, except for the right-hand side now, we have a beta, okay? I'm gonna call this beta, which is rate, okay? And then we'll see what that rate means. We'll just maybe start with a value of, I don't know, let's say 1 maybe. Yeah, let's just do 1, okay? 1 second. I'm just picking up some notes. Okay, let's just do beta equal 1.0. Okay, that's saying that the rate, it's a heating rate, so units would be kelvins per meter, right? So it's dt by dx. There's probably going to be a surface area involved. So we'll just take this as you know, 1 Kelvin per meter as we are heating the rod on the right-hand side. Everything else stays the same, okay, except we just added this beta. Now, we obviously have to fix our coefficient matrix. So the lower diagonal over here is all 1s, except for the last entry. It used to be 0, now it's 2. Okay, now that's 2. If you disagree, raise your hand or say something, okay? I want to promote dissent in the class. So for those who disagree, just speak up. Okay, so now the main diagonal is going to have, previously it had 1 and 1 at the end, and this quantity 2 plus delta x squared capital H negative sign. So that stays the same, but over here we only have to fix the first point, because the last point is actually minus 2 plus delta x squared capital H. So we don't change anything. See, it's really easy when we have the when we change to Neumann. And then the upper diagonal doesn't change. It's just all 1s and 0. Okay. If we had a Neumann boundary condition on the left hand and the left of the rod, and the Dirichlet on the right, then it's the upper diagonal that will change. Okay. And then finally, we combine as usual. Nothing changes. The right-hand side is all T infinity times delta x squared capital H. That stays. The first entry in the right-hand side is still T left, which is called here TXL. I'll fix those. And then over here at the last entry is going to be this quantity, T delta x squared, etc., minus 2 beta times delta x. So I'm just going to go ahead and put this in here. Okay. Minus 2 times beta times dx. And then the rest does not change. So we go from 300. Right. So now this is what you get. Okay. This is what you get. Now let me try something over here for my own benefit. Okay, so we're plotting t, dt by dx. Okay, and then if we put beta is equal to 0, okay. Okay, all right, so here's what I was trying. Since I know, I want to check my code if my code is right. So beta is 1 still. I'm going to let's keep beta as 1. And you know, you see this profile. There's obviously the rate of heat at the right-hand side just could throw you at any temperature, right? Because you're not specifying the temperature, you're actually deducing that temperature from the solution, right? But what you know is the slope at the boundary. So when I'm looking at the graph now, I can't tell if the slope is 1 or 0. It looks like it's 0, right? So I got nervous. What I did then, I said, okay, I'm going to make the slope, I'm going to make beta equal to a large number, like 100, okay, to see if I can make the curve kind of go up like this. And indeed, you run it, and you see the curve flatten upward, right? Saying that the slope is actually not 0, right? If you put beta equal to 0, then the slope is going to go to 0. Now you can go negative, actually. So you could be removing heat, okay? So minus 10, let's go to minus 100, okay? Look at that. So we're removing heat at the right boundary, okay? Anyway, play around with this. Feel free to play around with this. But the point is, it's no different than the Dirichlet case, except for these minor tweaks that we do to the coefficient matrix. Okay? Any objections? None overruled.
Can you scroll back up to,
Yes.
Can you scroll back up to where you're declaring your main diagonal?
Yes. Who's that speaking?
That's Eric.
Eric, yes, Eric. Okay, so the main diagonal remains the same as before. Notice, however, we only have to change the first point, not the last one. So I commented out the last one. And if you think about it, it's because we applied the governing equation at the right boundary, so at the last point. So that central discretization is still there. It didn't disappear. We didn't replace it with a fixed temperature value. Okay? If you're still trying to get it to work.
We're good.
Okay. Okay. Once you get to heat transfer with Professor Powell, you're going to be doing this in 2 dimensions. So make sure you understand how to do this in 1D. Okay? Okay, great. Now I am going to switch to the crown jewel of boundary value problems. And as we finish off, I'll finish as much as I can today, and we'll continue next week. All right, so I'm giving you now, it's same heat transfer problem. I fixed the boundary conditions at the left and on the right. We could put Neumann conditions, and you should be able to know how to do that after you review the slides. But what I changed here is the right-hand side. Rather than having t minus t infinity, now I have t to the 4th minus t infinity to the 4th. That's the equivalent of the radiative heat transfer initial value problem we did with the lobster. Now we're cooking the rod in an oven, okay? But we're looking at the distribution of the heat inside the rod. So now take the lobster and think it's at steady state, okay? And assume the lobster is this rod, okay? And then we're gonna look at how the temperature changes inside the lobster as it's exposed to this heating environment. So now I'm going to ask you to take a couple of minutes to discretize this equation at an arbitrary point I, okay, in the domain, inside the domain, interior point, t left and t1 and tn, they're t left and t right, so you know the equations there. What's left is everything in the middle. So I want you to discretize this equation at point I in terms of I minus 1, I plus 1, etc. and write it in matrix form or make a comment on what you observe, okay? While I eat a gummy bear that my son left me on my lap. Okay, time. All right. Let's see. Brendan, do you have an answer for us?
Like an answer is in what do I observe or the
Both.
discretization?
What is the discretized equation and what do you observe?
So if I'm understanding correctly, it'd be like u minus I minus 1, or I guess, sorry, t I minus 1 plus 2t plus t I plus 1
So
equals,
minus 2ti, not plus 2ti.
oh, whoops.
Minus 2ti. Yeah, ti minus 1 minus 2ti plus ti plus 1 over delta x squared, right? So that's, yeah, okay.
Yeah, and then equals the right-hand side, so alpha times t to the fourth minus t infinity to the fourth.
Okay, t to the, which t? At what point? So remember now we're discrete.
Yeah, ti.
Okay, so this formula, right?
Yeah.
Okay.
And so, I mean, my observation was just that that looks a lot like Euler's formula, but like for a second derivative.
So what is Euler's formula?
So it's our current guess plus the delta x times.
Okay. So I know what you're alluding to, but there's another way to phrase it, and you got to be careful about how you're describing this. Okay. So I'm gonna ask if someone else has a comment. So far, Brendan is correct. This is the equation, and I hope this is the equation you were able to obtain. Okay. By now, you should be able to know how to do this. All right. So let's see. What other observation can we make? Andy, are you with us? There's a very important observation we make here. I mean, this is just the heat equation, right? So can we just solve this?
Yeah, I'm here.
Yeah.
Personally, I don't really have any observations on this.
Okay. So then we can just put this in a linear system, just like we did matrix vector and solve it.
Well, Ti on the right-hand side shows up non-linearly.
Okay, so Paul, yes, that's right. So Paul and Salim, they're both saying that as well. And if you can see this, you should be able to see it. This is a nonlinear term. So previously, when we did t minus t infinity, everything showed up linearly, and we were able to turn all the discretized equations at all the points into a linear system of equations. However, this is a nonlinear equation because we are solving for ti and ti minus 1 and ti plus 1. And ti shows up nonlinearly over here. And if you were trying, are you guys still hearing me? Yes. And if you're trying, hello? Hello? Okay, great. There was some internet connectivity issues. Can you hear me now?
Yep.
Okay. All right. So this is a nonlinear equation. All right. So we can just put it in a just put it in a linear system, tridiagonal system, and solve it because it's a nonlinear equation. And if you cannot see it, actually, this is a system of nonlinear equations because at every point, except the T1 and Tn, at every point, you have a nonlinear equation that is coupled to a nonlinear equation at the neighboring points. So the equation at Ti is coupled to Ti minus 1 and Ti plus 1. And the equation at Ti plus 1 is coupled at Ti minus 1 and Ti and Ti plus 2 and so on. And they all show up nonlinearly. Now, we did cover systems of nonlinear equations, right? If you remember Newton's method. And we know how to solve this in principle. But can you imagine having 2,000 of these equations? Can you imagine the size of the Jacobian and how annoying that is going to be? I mean, it was one thing doing a system of 2 or 3 nonlinear equations, and that was annoying enough. But can you imagine doing this for a problem like this? It's going to be very, very expensive. Okay, we can do it. We know how to solve this using Newton's method. Okay, so this is a system of nonlinear equations that we have to iterate through, using guesses, etc. We would linearize it, etc., and solve it. But left untouched, it is very impractical. Left as is, it's very impractical to solve. Okay, and I probably have 30 seconds left. But there's a way to avoid the nonlinear solver. And what we're going to do next Tuesday, rather than having to do a Newton's method on all of this, what we're going to do, we're going to embed the Newton's method. Whatever that means, doesn't mean anything to you now. You'll see what we're going to do. We're going to embed, we're going to take the right-hand side, the nonlinear right-hand side, linearize it, and then iterate the entire system of equations as if we're doing Newton's method, but without doing Newton's method. It's much easier and much cleaner, okay? But what you should take from this is identify that this is a system of nonlinear equations, okay? Not a single, just nonlinear equation. At every point I, you have a nonlinear equation that's coupled to the other ones, and that gives you a large system of nonlinear equations. And with that, I will let you go. We will finish this off next week. I'll repeat what I announced early on. Make sure you go and take the quiz on acknowledging that you have a camera and you need to be connected to the camera for the final exam. The format will be similar to last time. It's going to be on Canvas, etc. Make sure you take the quiz to acknowledge that you're going to connect to Zoom. I want to be able to see you, see your face. And you're not going to be able to access the exam if you're not on Zoom, because I'm going to give you the code on Zoom, okay?
Mm-hmm. Is there another quiz besides that one?
Pardon me?
Are there 2 quizzes today?
No, there's just that quiz.
Okay, sounds good. Thank you so much.
Thanks, Katrina. Yeah, there's just that quiz. And make sure you just follow the announcements. Make sure you know when the exam is. Please come next Tuesday. Tell your friends and colleagues in the class to come next Tuesday. We need a high rate. If you want to help me, build feedback for this course and improve the course. I want you to come in big numbers next Tuesday. We're gonna have you do the feedback in class. You probably already have received links. Feel free to do those right now, but next Tuesday I'll give you time. We'll spend together. You'll spend time in class to fill out the survey for the feedback for the course, okay? But please try to come. There's going to be a couple of other activities. We're going to finish off these nonlinear things as expeditiously as we can. Then we're going to do a couple of other fun activities. And please spread the word, all right? And thank you so much for your attention. You've been a fantastic class this year, and you have a nice weekend. If you have any comments, stick around and talk to me right now. There's going to be a help session in a few minutes as well.
Thank you so much.
Thank you. Thank you.
Been a great class.
Thank you. Put it in the feedback.
No, I hated this class so much.
that is really
like this class is 0 out of 10. It's like the professor said, "Oh, it's great."
No pressure. All right.
The extra credit if you get good reviews. I'm joking. I'm joking.
I don't know. I don't see the reviews until the class is actually